Projects. Turn them in. You got them here? You got trim in the box or what? Did you? Do they fit? I was supposed to mail around saying you could bring them, turn them in here if you wanted to, in case the box wouldn't fit everything. But yeah, turn them in if you got them. I'll take them here too as well. So how was it? Project 1. Okay, now you're designers. All right. I guess we're going. I should go here. Let's start up here. What I'll do is we'll try to grade them relatively rapidly as soon as we can. And also we'll take some of the best ones and kind of talk about them a little bit for you so you can sort of see what comes out. You'll see what I think it'll be pretty enlightening. I'm sure some people came up with some interesting designs, and we'll see what they are. So I was going to, if I had them here, I was going to get the figure of merit numbers and take them off, but since I only have one project, I guess I won't won't do that, right? Okay, so any questions or anything about the whole project process? Now that you're just finished with it, any feedback or something like that we should think about on the next projects, or just went so smoothly and straightforward? And the schedule is, I think you probably know it, but I'll give it to you. Hopefully later today, our mail system's kind of fouled up, so I haven't been able to check out the homework. But we'll probably turn out a homework in today. It'll be due the following Wednesday. Following Wednesday, we'll actually collect this homework and hand out another one, which won't be due for 2 weeks. Okay, so you'll have it. You can do it before or after the midterm, depending on what you want to do. That may get delayed a little bit too. We may not even hand it out, I'm not sure, because you won't have all the material yet. So then we'll have the midterm in 2 weeks, okay, on Wednesday. It'll cover everything up to frequency response, okay. So basically through the lecture today will be the last material that will be on the midterm, okay. So that'll be we'll start frequency response next lecture. It'll be comprehensive. You can look at the old midterms. There's a lot of them online, so you can sort of see what they're like. Their analysis, and if you did the project like I asked you to do it, which was really understand the circuits that you're designing, and do them by get good hand calculations. The midterm should be fairly straightforward because it'll be basically just exercising those skills that you should have developed recently. Then we'll have another project then, okay. A week after the midterm, we'll hand out a project then that has frequency response. So basically the circuit you did now, but then we'll put in speed requirements. Okay, so it'll have to work at meet some frequency response requirements. It'll have certain gain at some frequency, up to some frequency. So we'll give specifications on that. And then the only thing left after that then we'll go into feedback. We'll do the feedback and stability, and that'll be the final project where you put feedback, stability, frequency response, DC analysis like you did this time all together, and that's the final project. Okay, so any questions, issues? What's going on the rest of the term? Anything about the midterm you'd like to know about? I'll do a review on the midterm in a week or something like that, right? Okay. Just tell you what's on it. Just kind of go through all the material. I'll tell you what I think is the most important points. Okay? Okay, so what we've been talking about, I'm going to finish up today, is this output stages and do more complicated op-amp analysis, okay, let me just, so this output stage is a little fractured because I wanted to get to an output stage you potentially could use in your project. So I'm sort of skipping around a little bit here. Hopefully it isn't too confusing. Page 13. This is the common drain output stage, the good old source follower sort of thing. Basically what we're just talking about here, I mean the MOS version of this, of course, is it's a current source with a load, right? And this is minus supply, This is plus supply here. And the thing that gets a little bit confusing on these things is the fact that this is returned to ground, or half the supply, like in your project. And that, I think you're well aware now that what has to happen then is that you've got to not only, this current here is set by what the negative, let's call this IQ, the negative voltage that you can achieve is going to be the case when there's no current flowing through this. And it's going to be equal to minus IQ times RL. Or if this current source goes into linear region, that's the two, so it's the maximum of those two values. So, and then of course what this then has to provide is not only IQ, okay, for this current source which pulls the circuit, pulls the output negative, but it's also got, when you're trying to go positive, it's got to supply current to the output. So you end up with having to have 2 IQ go through this transistor when in the positive mode. As I mentioned last time, there's a constant current going through this circuit of IQ all the time. It goes from 2 IQ then down to 0, basically, for this transistor. And we call this sort of class A. So this is a class A circuit. Okay. So, and you can do a bipolar version of that. The big advantage of bipolar is that you can, we can only go as high as a VD sat, or actually it's worse than that for this case, right? Because if this voltage can only go up to as high as VDD, the input to here, because it's coming from some other circuitry which is attached to the same supply, then this voltage, the maximum voltage it can get up to, is VDD minus VT minus VD sat of this transistor right here, right? So that's an issue which is bad about this circuit, and as you know, you can't really use this for your project because the VT alone dropped you down below the voltage swing that you could live with. So that's all issues and problems with that circuit. So we talked about inverter range. I already did this. This is this common source configuration with a current load down here. Okay, and I went through that already. Okay, so what's the new one I want to get to? New one is, let's do something really different. And this is your output stage, though, is a lot of pain, and as you've probably seen, depending on how you did the output stage, the transistors at output stage dominate your entire figure of merit quite easily. Okay, and that's not actually, you're driving a pretty easy load. 1 kilo-ohm is actually quite straightforward. I mean, I think if you look in the projects from last semester, you'll saw I required you to drive 50 ohms. So just think about that. If you would have 20 times more current coming out of your output pair, what would happen to that output stage, right? It could be pretty big, right? And so, and efficiency is a big issue. You know, how much power you dissipate in the output stage versus how much gets into the load. So here is a class of circuits that actually are much more efficient. Okay, so this is when you really want to put out power. This is the way to do it. I mean, as I went, I think in the last lecture, I kind of indicated that you can come out with a really low efficiency number, right? Power to load over power in the circuit, when I included the bias string. But if typically a class A, okay, kind of limits out about 25% efficiency. It's hard to get above that, even if you have no current going in, you don't count the current going into the bias circuit. Okay, it's difficult to get above that. I think it's in the notes I derived that. This class B circuit is able to do up on the order of 70%. Okay, greater than 70%. So how does it work? Okay, so here it is, and basically it's 2 circuits connected together. The way to look at this circuit, here's the input, here's the output, here's our load. We're going between plus and minus supplies like I just showed a second ago. The way to think about this is that one of these 2 transistors is going to be turned off, being cut off, depending on what the input voltage is. Okay? So the way you can look at this circuit is in 2 modes. Mode 1 is M1 is on and M2 is off, and I'll derive what the voltage is that turns these things on and off. So you can put your finger over M2, okay? So what do we have left? We have a source follower, okay? And what the different situation is we have now than I just showed you a second ago was I had a current source down here to pull this negative, but since this transistor is turned off, I don't have to supply any current through this upper transistor into this lower circuit. Okay. In fact, let's look at the 0 voltage condition. If the input is at 0 volts, and let's assume, and let's try to figure out what the current is that's going into the output here. If this is at 0, what's this upper circuit doing? Can you tell me what state this transistor is in? Saturation? Okay, let's check. Let's do all the checks now. Check cutoff. Let's check for cutoff first, right? If this is at 0 and this is at 0, what's the voltage across VGS? 0. I mean, that'd be the thing. I mean, if you got 0 volts across VGS, that means you can have no current flowing. That means there's no voltage drop across RL. So the 0 volts is going to appear right across VGS, right? So it's a consistent solution. So in other words, 0 volts across VGS means if VGS is less than VT, things in cutoff, right? No current. So that means there's no current flowing through this upper stage. Now let's look at the lower stage. So what is that? It's actually also a source follower. It's a source follower with a p-channel device. Okay? Just it's one upside down, right? So you start off with a ground resistor to a minus supply. All right? So here's V in and here's V out. So looking at this lower circuit, that's just a common drain circuit with a p-channel device. Okay, what about it? What's its situation when V in is at 0? Same thing, right? You got 0 volts across this VSG, okay, in the other direction, right? And so 0 volts across here, across from here to here, means there's going to be 0 volts across here. 0 volts across here means this thing's in cutoff, means there's no current through here, so we're consistent. So this means this transistor is also cut off. So with 0 volts on the input, there's no current flowing in the output, and therefore this output's at 0 volts. Okay? Now, what that tells us is that we're in a different kind of operation than we talked about a second ago. This has no current flowing when the input's at 0. So we call this class B. Okay? Because class B is actually, it's not only at 0 that we have no current flowing. When does current start to flow in this output? So let's start going up with V in. As we go up with V in, and take my word for it for a second here, M2 is going to stay cut off. Let's watch what happens on this upper stage. As this voltage goes up, when does this transistor go out of cutoff? VT, exactly. VT. Get used to that. It's kind of a, you gotta. This is one of those things that ought to just get used, in part of your being, right? In other words, this transistor cannot turn on until there's at least a VT between the input and ground, right? You might say, well, what's the voltage drop across this resistor? But as long as the transistor is cut off, there's no voltage drop across here, right? So in other words, way to think about it is that there's no voltage drop across here. So what's going to happen is V in will drop across this VGS. It will be equal to VGS until this transistor turns on. So all the voltage drop will come across here. This will stay at ground. This point will stay at ground. So you get full VT. So V in has to go up to VT before this transistor can turn on. So in other words, as we go up here, this stays at 0 until this input gets above VT. So we can plot that. So we plot it right here. Let me plot it right here. Okay. So here's V in, here's V out, and as we go up with V in, until we get to VT, there's no outputs at 0 volts. As soon as we hit VT, then this device turns on, and it's in saturation. And so then what happens, it's just good old source follower. What happens to a source follower? It has a gain of nearly 1, so it goes up. So the V out versus V in of this circuit in the positive direction is equal to just like a source follower. What's happening to this PMOS common drain circuit, source follower, in the bottom down here? Let's look at this. As this voltage goes up, what's happening with this transistor here? It's getting more and more cut off, right? In other words, this voltage has to go in the negative direction relative to ground in order to turn this transistor on. So the more positive we take this input, the more this guy cuts off. Okay? This guy just stays off. So this is our output then. We don't have to worry about what's going on with this bottom guy. Let's flip it around. Let's look at the other way. Let's go negative with Vn. As we go negative with Vn, soon as this gets a VT below ground, then we have this VSG is negative enough to turn on this transistor. So we go in this direction. So this is VT in. This is VTP. This guy turns on. It goes down. Let's look at what's happening on the upper transistor when we go negative. If we take this negative, what's going to happen? As this goes below ground, this thing for sure stays off. It goes more and more in deep cutoff. Okay? So this is your output. This is class B. Yeah.
Is that possible, like, when we turn the top transistor on, then there will be voltage at V out? So, like, in that case, then the lower PMOS will have any chance to turn on because it's not relative to ground anymore.
Okay, so what happens with V out? This voltage goes up, okay, as V out goes up, and okay, let's look at. The answer is no. Okay, right. So let me show why. Okay, so let's go over the PMOS side. Let's the NMOS side. That's easier for me to do always, right? So you're worried about the let's take input down, and you're saying V out is going to be going down as well because it's being pulled down by this PMOS channel device down there. So the issue is, can this device ever turn on? And you can see what's going to happen here. This guy doesn't turn on until it's at least a minus VT below ground, right? So this voltage here, this needs a plus VT relative to this to turn on. So you got a 2 VT drop across this gate to source here in the wrong direction, and so this guy stays good and hard off. Right? But notice there, that's important. There's this 2 VT thing that's sitting across here. That's kind of important to us. It has to do with this issue right here. So if we plot a signal, so typically what we're trying to do is we put in an input voltage, let's say it's a sine wave like this, and we go into something that has a transfer function like this, where it has a dead zone here. What is the output going to look like? What's going to happen is in the region plus and minus VT around ground, this is plus VT to minus VT, and here's 0 in the center here, the output is going to have 0 output. So if this is what the input, what does the output look like? It'll be a little less gain, little less than 1, so it'll be a little smaller than this. And it'll also, in the positive parts, it'll go up just fine. But as soon as it gets into this region right here, the output's going to go flat. Then it's going to go around bottom, and it's going to go flat again. And this is the plus and minus VT points. Okay. This is called crossover distortion. So around 0, you begin to have this kind of nonlinear response occurs, and it'll cause harmonic generation. If you were listening to this, you had this was used in the output of your amplifier for your stereo system. What's going to happen is that you're going to hear all sorts of high frequency noise show out of this thing. So it'd be a lot of very high harmonic distortion. There's a couple answers to this. One answer is, which we're going to see a little bit later after the midterm, is when we put this into feedback. In other words, we put this as the output stage of our amplifier, and we put feedback around our amplifier. It's going to take, what will happen is this distortion will be eliminated. I'll use this before, and I'll begin to start talking about feedback now. Feedback, negative feedback like this, sort of makes everything better. Okay, kind of a rule. Okay, if you want to figure out what direction is going to happen, probably what's going to happen, everything's going to improve except for the gain. What we'll do is we'll trade off gain of this amplifier to improve all sorts of other things associated with this circuit. That's why this op-amp configuration is so important. That's why it's such a critical building block of everything we do. A to D converters, filters, D to A's, drivers, amplifiers, everything. Quite often we try to use feedback if we possibly can because it makes everything better. I won't explain why it works right now, but this distortion, which would be very damaging if you wanted to listen to this, you would think, if you put it in feedback, this crossover distortion will be eliminated, so we'll talk about that later. But let's say you don't have a lot of feedback. Is there a way we can remove this crossover distortion? And there is a way you can do that by changing this circuit, and I'll show you that in a second. Okay, so this is class B because it's more than just right at the edge. It's what we're going to, if we could make this so we don't have this crossover distortion, but still have zero current flow, we can get what we call the class AB operation, and that's what I'm going to show you right now. Okay, so here's the analysis of this. Effectively, it's just to analyze this, how high, what's the maximum positive swing you can get? Well, the maximum positive swing, if this is up equal to VDD, this, just like I said a second ago, can't be higher than VDD minus VT minus VD sat of this transistor, transistor 1. So this is V max. V min is minus VDD plus VT of 2 plus VD sat of 2. So this thing is limited in how high it can go, V out plus and V out minus, depending on how big a transistor this is, because this VD sat will limit your maximum positive swing or negative swing. Okay, so it's just typical two source follower analysis you need to do to figure out the positive and negative swing. So V out minus and V out plus. What I did here in the notes was just, given that you have a V out plus and it's greater than, let's say V out plus, and let's say it's less than VDD minus VT, because you can't do anything about that VT, you can make W over L larger and larger and reduce VD sat as much as you would like at the expense of bigger and bigger transistor here, right? If you're driving 50 ohms, this guy can get pretty big if you want to have a pretty big swing out here. Okay, any question about that? So that's basic push-pull operation. All right, how do we remove that dead zone? So the problem is we got a curve that looks like this, right? Comes in here, flat, goes down here. So this is V in versus V out. Here's the push-pull circuit. Yes?
Now you have a PMOS on top and an NMOS on bottom.
It's because it's wrong. Good eye, right? I got to change that in the notes, and I keep forgetting to, right? Right. Yes. That's a very different circuit. Right. Thanks. Yeah, I got to fix that. Okay. Now, we're back to the same circuit, right? Push-pull. Here's our ground. But now what we're going to do is change the input. The problem we had was, okay, remember, was that when this is where the NMOS device is on, right? And PMOS is off. And this is with the NMOS off and the PMOS on, okay? So what we want to do here is basically kind of slide over one of these relative to the other so we get a continuous curve. In other words, just when the NMOS turns off, we want to have the PMOS turn on. So how can we do that? what we can do is we can put a little battery here, right? And effectively all we're doing is, this is two diode connected transistors of size VT plus VD sat. VT plus VD sat. Probably should, they're not going to be exactly the same VTs, right? So what we're doing is we're taking the output that's going to the P channel device, adding to it, so this is, let's call this VG3, the gate voltage going into the lower P channel device. This voltage up here is going to be VG3 plus VT5 plus VT4 plus VDSAT4 plus VDSAT5. Now if we make these VDSATs 4 and 5 pretty small by not having a lot of current here, okay, we can make these pretty small relative to the VTs. Then I basically have a VT4 plus VT5 offset to the gate of the N-channel transistor relative to the gate of the P-channel transistor. So in other words, soon as the P-channel transistor turns off, because I've added a VTN, a VT2 and a VT3 to the N-channel side, it's actually not this direction. What I've done is I moved this way. So I've moved this curve here. So as soon as the N-channel turns off, P-channel turns off, the N-channel turns on. So now I have a continuous curve. I don't have this crossover distortion. I still have the situation where I have zero current at zero input. This is good. I have an offset here now, though, right? Vn has to be offset by a Vt, in order to get 0 volts output, I have to have input at Vt5, right? I mean, there's the, this thing goes positive when Vn is equal to minus Vt5, okay? Is this a problem? No. If this is at this tail end of an amplifier, if we've got a couple of stages of gain, let's say this is our output stage, so this is our push-pull output stage, okay? Let's say this has a gain of 1,000. Let's say this is 0.3 of a volt. Then the offset we're getting from this output is 0.3 volts divided by 1,000, or 0.3 millivolts. So having this little offset here, in fact this isn't symmetrical, is no big deal at all, right? I mean, I could have somehow configured this in such a way that I drove these two things symmetrically, but like we just talked before, offsets after a large amount of gain is just insignificant because you just put a little teeny offset voltage right here, right? And that takes care of this little offset we have here. Okay. Okay, so how do you derive, how much current flows through this circuit at this point right here? There is some current flowing through it. These transistors are going to be quite large, right? Because if you're driving a small resistance. So even though I said these VD sats are 0, they're probably not 0, okay? Any little overdrive voltage applied across these gate to source here is going to give a lot of current because these WLs are so big. So it's an easy little calculation for you to figure out how much current is flowing through here at the zero bias output condition. There'll be some current flowing right down here, depending on how much current you're having flowing here and how much voltage drop across here. And how do you figure that out? Well, it's pretty simple, right? It's just you go around this loop right here. You have Vt of 4 plus Vd sat of 4 plus Vt of 5 plus Vd sat of 5 equals Vt of 2 plus Vd sat of 2 plus Vt of 3 plus Vd sat of 3. So the VTs of the N channels and P channel VTs will probably cancel out. So you have Vt sat 4 plus Vd sat 5 equals Vd sat 2 plus Vd sat 3s. If you got the W over L's and you got the current that you set here, whatever this is, I ref, let's say, right? So you have the current for these VD sats here. You can calculate what the current is flowing through the straight through current here, let's call this I straight through, okay, from these two eyes. Really easy calculation. I see that? Gone. Okay, so this idea of a level shifter is actually pretty useful. It's being used here, but if you need to do a big change in voltage, this is the old battery thing. Well, we've used this before several times now, right? Put a current source in series with a diode-connected transistor, and you basically get a little battery that connects between those two voltages. We use that for the high swing on our current sources, okay? And so you can use it here as well. And it's useful just in general. So it's a little technique to always, this is a VT plus a VD sat. Okay. Okay. And this I talked before. Let's calculate efficiency of this circuit. Okay, so this is a little more complicated than the source follower, than the source follower with a current source. Because at 0, for this, the source follower case, which I kind of went through pretty quickly. Let me just review a little bit there, what happened there. For this case, what happens is, if we look at the current coming out of this positive, it's all, and this is the negative supply, right? It's always IQ, so that doesn't change. This goes into ground, this is RL, so there's no power dissipated going into this ground. So it's VDD where we see something change. So we always have IQ times VDD associated with this. But if we put a sine wave in the input here, what happens on the output? We get a sine wave here as well. What's happening to the current? It's clearly it's 0. There's IQ flowing here. So this current coming out of the upper supply, let's call it I positive supply, okay. It starts off when the output is equal to 0. Let's call this, this is V out. When the output's equal to 0, the upper supply current is equal to IQ. So this is IQ, right? Because if this is at 0 volts, then this upper has to supply this current here. So we just have IQ. Now what happens when V out increases? This is kind of how I want to do this. So as V out goes up, okay, we've got to begin to supply current through this upper leg here, right? In fact, when V out gets up to V out max, and let's say that's equal to IQ times RL, what's the current going to be in out here? Well, it's going to be 2IQ, okay? Because you've got to have IQ flowing here, and you've got to have an IQ flowing through here to bring this up, a voltage drop across here of IQ times RL. Then what happens when you go the other way is, and this is where V out is equal to, this is a very weird plot. This is versus time here, right? This is time in this direction. Let's call this plus IQ times RL, and this is minus IQ times RL. So this, at this point right here, this is time in this direction. I'm plotting. At this point here, V out, so this point here is where V out is equal to IQ times RL. This point is where V out is equal to minus IQ times RL. How much current is flowing through this upper transistor when this output is at the most negative voltage? Who can tell me that? Most positive voltage here, when this is IQRL, I have IQ flowing here and IQ here, so I have 2 IQ. When this is at the most negative, at IQ minus IQRL, how much current is flowing out of this positive supply? None. Right. This, what's going to happen here is that all of this current, this has to be at minus IQRL right here, all of that's being supplied by this lower current source. That means there's no current coming through this upper transistor. So this actually goes down to 0. Well, notice this is symmetrical. There's times when this goes up to plus 2 IQ, which is IQ more than the bias, the sort of the DC condition, or the nominal condition, and it goes down to 0, which is 1 IQ less. So if you look at sort of the area underneath here, the power on the average, that's kind of how I did the calculation the other day, is this is going to be the same as if we just had, coming from this upper supply, it's IQRL on the average. This is IQ average, right? So this is how much I from the positive supply average is equal to IQ, okay? So the power of this dissipated in this output stage, as this output swings back and forth, will be equal to 2 times IQRL, okay? Now, this is a very different situation with this push-pull circuit. This is the output going between V out max and V out minimum, okay? If we look in the upper transistor, okay, let me put the crossover distortion in this for a second, right? It's not that. If we look at the upper transistor, when it goes all the way up to the positive, this guy's turned off, and we have current flowing from the upper side. And how much current do we have flowing from there? Well, it's exactly equal to V out over V out's at this node here. This is RL. So the current coming from here is just going to be V out over RL. So if this is the swing of V out, this is the current coming from the positive supply. It's going to just follow the input and the output, and the current value will be V out over RL. When we go in the negative direction, then we have this current from the negative side, and the upper transistor is off, and the bottom transistor is on, and we get this bottom one. So what's the amount of power being dissipated? What you have to do is you've got to integrate for this supply, and so it has, you know, from 0 to 1 period. We've got to integrate over this half a sine wave. This is efficiency is usually calculated for sine waves. Okay, let's just say that's true. That's kind of a definition. Okay, efficiency of sine wave input. That's very typical. So this is what's coming out of the positive supply, and this is what's coming out of the negative supply. So we have to add those together. So it's kind of I supply of the, this is for each one of these. And this is, so I supply positive is going to 1 over time, integrate a half a cycle. You end up with this is the answer. When you integrate the current, you get the average value of the current over this half a cycle. Do the same thing on the negative one. You get an average value there. Of course, those two are the same, so I just put a 2 in front of here. So I get 2 times this average current times VDD gives us the power coming from the supply. What's really nice about this, notice, is that with 0 input, we get 0 current. We have more output current being supplied to the load. We get more current coming off supply. That's how we'd like to have it, right? Remember our Class A thing, we had tons of current flowing. We had no output. We had twice the amount of current we had flowing, you know, and so I was kind of just, you can see how inefficient that approach is. This one's really nice, right? It just goes to 0 and output 0 and so on. So this is the amount of power coming from the supply. The amount, if V out, this is peak. V out is equal to V, the peak value of V out, right? What can it be? Well, it's got to be at least a VT plus a VD sat below the peak value. But let me just, okay, so let's leave that in there. So here's the peak value of the load we have. So the efficiency is this number right here, 1/2 times V out squared over RL, divided by the power from the supply, which is this number right there. And you end up with a number that looks like this. Pi over 4 times V out peak over VDD. Now remember, V out peak can't actually get all the way up to VDD because it's going to be less by a VT minus a VD sat. But let's say we had a process where VT is equal to 0. It actually happens. I mean, any given, typically especially these days, they're giving us multiple transistors with multiple VTs. So there's a 3/10 volt VT like you have, but you also might have another transistor that has a 10th volt VT you can play with, or sometimes even a 0. Okay, so let's say you had that kind of process where you could use that kind of output device. So VT was 0, and you made the VD sat really huge. I mean, really small by making the WL really big. V out peak may get close to VDD. So then the limit that we can get of efficiency of this circuit comes out to be 79%, almost 80%. Greater than 70%, I said. So this circuit is actually quite efficient. Okay, really good for power efficiency. So if that's part of your figure of merit, and you're driving a lot of current, You got this output swing problem because if you have big VTs, that's going to knock down your output swing. But these push-pull things are really good. Okay. Any question about that? That's kind of that's it for push-pulls. Any question about that? Going, gone, break. And we'll do some complicated op amps after break. Sleepy people today, I see. Okie dokie. Let's roll 'em. Sleepy people today. I really probably should have a very easy lecture after a project's due, right? Okay. Well, this will be, I think, interesting. Okay, so this is actually, the circuits I'm going to show you today are some of the really standard MOS circuits used, okay, and for op amps, okay. It's they're very straightforward, they're very simple. Here was the two-stage Miller op amp. I think a lot of you use that or something very near this for your, so you have this differential pair followed by a second output stage. Now, you needed this two stages because if you try to tie that 1K ohm right to this point right here, you knew you were in trouble, right? You couldn't get enough gain out of this stage. Fortunately, quite often in actual circuits on chip, we don't drive resistances, which is really great. You think about it. I mean, quite often what we're driving is other MOS circuits, and even for things like filters and A to D converters and all this other stuff I talk about, what we'll often be driving is capacitors. Okay, so this is actually what made MOS so straightforward to do is that we can put capacitors, they take area, not quite as much as resistors typically. I mean, of course, it's farads versus ohms, but we don't, you can actually, the size capacitors you need to do circuits don't really consume a whole lot of area. And so quite often what we'll have is the amplifiers we have will be driving capacitance values. If it's connected to another circuit, you know, another amplifier, let's say, I mean, that's driving into this gate here. What's that? That's a capacitance as well. I mean, it's the gate capacitance of this input transistor. So typically what we do in MOS is drive capacitance. Okay? Now, if you're driving capacitance, you may ask yourself, two stages are a pain, right? You got to bias it up and all sorts of stuff. If I really don't have a resistance to drive, can I get everything I need in one stage? Can I do everything with just one differential pair? Well, you can get a certain amount of gain. I think you probably know, you've got a feel for that now probably, all right? And particularly if you can't drop the current way, way down because you have to drive some capacitance, right? You know, capacitance requires some current to drive, make a voltage change, right? So you can't reduce the current to get gain way up. So you'll end up with sort of a limitation on how much gain you can get out of this configuration. Well, how can we get more gain? Well, one thing we can do, and I mentioned this to you last time, right, is we can cascode this. We can cascode the upper transistor and lower transistor. We've got to cascode both of them, right, in order to be able to get enough to get, because output parallel resistance of the upper and lower stages. So here is a circuit we might talk about. Okay, so let's look at this. It's just a single stage differential pair. Here's the current source, the tail current source. Here's the driver transistors, and I've broken out the differential input and common mode input. So that's all this little network here is just, you know, showing differential and common mode separately. Okay, so this is just our two inputs here. The input plus on this side, and this is V input minus on this side. Okay, I've cascoded the bottom transistor, so this is just the cascode transistor, and I've biased it with this transistor over here, which is very weird because I don't have a connection here. Okay, so I'll put a connection in. Okay, right? So I biased it up with this string on this side over here to bias up these transistors over here. So this is the cascode for the lower. Here's the output. Here's the cascode for the load, M6. And here's our good old current source load connection that we've had in the past. So M6 and M8 are cascodes to increase the gain. So what's the gain of this circuit? If all these devices are in saturation, you can write down the gain, right? The gain of the differential mode gain of this circuit is going to be GM. Let's say our RO is the same. All our O's are the same. Is that it? Times squared, right? I mean, the R out of this circuit is going to be looking into here. We'll see a cascoded upwards, so that'll be GM over 2, right? GM R0 squared looking upwards, right? R0 up. Let's call this, you know, it's basically GM6 and R04 times R06. I mean, that's really what you see looking up. Looking down is equal to GM8 times R02 times R08. I mean, this is the source degeneration of this cascode stage, right? Right, so looking downward, you see basically what do you have? You have, here's M8, and in its source, this is a virtual ground, remember? Okay, roughly a virtual ground. This, I'm making this approximation now. I mean, of course, this is not a balanced circuit, but if you go through that whole analysis I did before where we were accurately, you know, you calculated this and have these transistors identical to these transistors, then remember, it just turns out to be a parallel combination of this and this looking down, right? So I'm using that fact. So this is R02 down here. So this is not truly a virtual ground, but it acts like it, right? It's a little nasty there. Okay, so this is just source degeneration looking down here, right? So that's just the cascode. That's how we get this value. So if R zeros are all the same, the GMs are all the same, you end up with this as your answer, okay, for the differential gain. It's GM of these transistors, GM2, which is equal to GM1, times R out, right? And this is equal to A differential mode gain. So lots of gain. We got gain like of 2 stages in 1 stage. What's the problem with this circuit? Swing, right? Okay, so this is great if you had 5 volts to play with. This is not so great if you have 1.2. And this actual configuration here is a poor strategy for biasing. So I'm showing you this just for the purposes that how can you quickly figure out what the swing is that's valid on this output. Okay, that's the reason I'm using this. This is not a good way to bias up the circuit. We'll see why in a second. So here, so the small signal gain of this is pretty straightforward. The more interesting design problem here is what is the, oh actually I didn't do this. Oh, wait. I didn't tie this off here. I actually biased up this transistor here through this string over here, right? So this voltage here is coming from this string. But these transistors track these transistors, right? I don't know why I did that. This would be the same, but whatever. Okay, so now let's figure out what is the swing at this output. In other words, how far in the positive direction it can go and how far in the negative direction. So what is the swing in the positive direction? Hopefully from your project you're comfortable with doing these little calculations. What you need to figure out is when does this guy go into linear region operation? How do you figure out when he goes into linear region operation? To me, the easiest way to do it is you figure out what the voltage is on its source, okay, and you know you can go up to within a VD sat of that voltage. So what's the voltage on that source? Well, can you figure it out by going across M4? No. Right, you should know that, right? You don't know what the VDS is. It's going to be set by something else. What's it going to be set by? Well, you got to look around to figure out what's setting it. Looks like here's a bunch of diode-connected transistors. I know what those are. Those are like little batteries, right? So I know that this voltage here is going to be VDD minus VT of transistor 3 minus VD sat of transistor 3. That's the voltage here. Well, that voltage sets the drain of M3. So I know the drain voltage of M3 now. So what's the voltage here? What I'm going to do is around this loop. I'm going up to here, then to here, and then I'm going to come back down here because these are all VGSs. And if we're in saturation, we know what the VGS has to be. Right? So we go to here, and we go to this point. We know the voltage there. So here we go up or down another VT plus another VD sat. So this voltage is going to be VDD. Let's call this equal to VG3, right? It's going to be equal to VG3, the voltage here, minus VT of transistor 5 minus VD sat of transistor 5. Okay? Now we go back up again because here's what we really want to find. Okay? So we go back up. What's this VDD? Okay, so this is V at G6. This is the voltage on the gated transistor 6. VG6 equal to this. Right. Now I want to find V source 6. Well, it's going to be VG6 minus or plus VT of transistor 6 plus VD sat of transistor 6. Okay? So you kind of go around this loop to find out with this guy here. Then what's the maximum voltage I can have here? It's going to be 1 VD sat below V source 6. So V out max is equal to V source 6 minus a VD sat of 6. All right. So let's let all the VD sats be the same. Let's let all the VTs be the same. Okay, all right. So what do we end up with here? We end up with this point right here. Let me just get some paper. Paper. No paper. Okay, come back to this. Okay, so V source 6 is going to be end up equal to VDD minus VT. Let's see. Could go up a VT plus 2 and back down 1. So minus VT, a minus VD sat. Let's say all the VD sats are the same, all the VTs are the same. Okay. So V max out max is equal to V source 6 minus VD sat. Okay, all the same. So this is going to end up equal to VDD minus VT minus 2 VD sat. Okay? So we figured out what the maximum positive voltage is here. Let's go in the other direction. Okay? How do we figure out how far down we can go? Okay? What we need to do here is we got to figure out what is the voltage at this source. Well, this source, I mean, these two transistors, assuming they're tracking the same current through here, and I bias it up, this has 4 over 1, this is 2 over 1. So if this is 2 I ref flowing through here, this is I ref flowing through this leg, and it's I ref flowing through this leg. So these have the same transistors, they're the same size. So this voltage here will be the same VD sats that we had for this leg here. So let's say all the VD sats are the same. So we know VG8, what's it going to be? Let's calculate VG8. VG8 is going to be equal to VDD minus 2 VTs minus 2 VD sats to get down to here. So it's minus 2 VTs minus 2 VD sats. Okay? And that voltage is what's applied exactly to this VG8, right? Through this diode connection right here. So that's the voltage we have right there. Okay? So now what's the source here? So let's call V source 8 is equal to VG8 minus a VD plus a VD sat. Wait, no, V source 8 is VG8 minus VT, go down another VT minus another VD sat. Okay? Now, V out min has to be 1 VD sat above the source, so that's going to be V source 8 plus VD sat of transistor 8. So they're all the same. Now, let's put that together. I end up with VG8 minus VT minus VD sat plus VD sat. So V out min is equal to VG8 minus VT. And VG8 we said was equal to VDD minus 2 VT minus 2 VD sat minus a VT. Okay, so let's look at V out max is VDD minus VT minus 2 VD sat. V out min is VDD minus 2 VT minus 2 VD sat minus a VT. So what's our swing? VT, just VT. Here's the maximum voltage, here's the minimum voltage. It only differs by 1 VT. So this bias condition only allows this output to swing 1 VT before one of these two devices go into linear region operation. Okay, to see how I did that. I mean, this is not that interesting a circuit. But what's important here is the way I did all of this cruising around, figuring out what the voltages were. Any questions about that? This is really, hopefully you learned this in your project. Yes? I thought it was 2V2 too. But it came out this, why you say? Okay, that's... Oh, I see. I'm sorry. It's not 2V here. Okay, you're right. So it's 2VT, right? Okay. Let's just write this. You're right. VDD minus 3VT minus 2 VD sats. Right. So this goes up as minus VT, and this goes down to minus 3 VT. So it's, yeah, so it's 2 VT, right? 2 VT swing. Right. The really weirdness about what I just did, okay, it's what I'm really relying on is this self-consistency in our calculation, right? The fact is, I'm assuming these are all in saturation. If they're all in saturation, then they have to have this VGS that I'm talking about, if they have the currents that we've set by these current sources. So once I know that, then I can use these like little batteries. Obviously, they're not little batteries, right? I mean, the gate doesn't set anything, right? The gate's an open circuit, right? I'm just relying on the fact that this has to be that voltage. This is how that bias will work out. I think I mentioned this to you before. It may seem reasonable to you, but at some point in time you're going to say, geez, how can that be true? It's just, you know, if I know, you think about it. If I have a current source driving, you know, this transistor like this, I claim that I know what this voltage is. It's VT plus a VD sat. But this is a gate. It doesn't set anything, right? A gate's an open circuit, right? But what I'm really relying on the fact is that this device is in saturation, and if I know the current, then the only possible voltage that has to be across there is VT plus VD sat. And if any other voltage is there, this device is either not in saturation or it's not having this current. But for this configuration, it has to have that current, so then the only other choice would be that it's not in saturation. Then, if it's any other voltage than this value right here, it'll be linear, it'll be cut off. Really important point. If you have any troubles with that, please talk to me. Hopefully you got that clear. So I did this in the notes. You can... Okay, so let's do a better one. Where are some problems with that circuit? Okay, a big problem was in the swing and the downward side. And plus there's another issue here with this circuit. What happens if we begin to bring, for V, let's do common mode swing on the bottom. Let's say VIC goes positive. What's going to happen? As this voltage starts to rise, this voltage is fixed. What's going to happen to this transistor? This voltage is fixed. This guy, when he gets up a little bit, this guy here is going to go into linear region. So you have very poor common mode range on this device. You can't raise this very high because this guy is fixed by this guy, by this bias I set up over here. See that? So is there a way that we can do this better? Yes. Here's what we're going to do. Instead of biasing this from an external string, what we're going to do is to put we're going to put a little battery between this source and this node here. We'll bias it up with this little current, so this actually acts like a battery, our typical little trick. This extra current, which will be much smaller than Iref typically, okay? This will be a much smaller value, because all we're trying to do is bias up this little battery thing here. That's what this current source is here. So this voltage here will be a VT plus a VD sat above this source. So now, what voltage would we like that to be? So let's call, notice what we'd like to do. If we bias with IB with the same current that we had here, or 3 times, that we have going through this leg. So maybe let's say, oh, it's Iref. Okay, so if I made IB equal to Iref over 2, I'd have to make this a little more current down here, but that's okay, we can do that. And I made this transistor the same size as this one right here. It's 2 over 30 shown here, but let's say I made it 2 over 1 instead of 2 over 30, okay? Then what would happen? I'd go up a VT plus a VD sat, I'd come down a VT plus a VD sat, it'd be the same VD sat, then the voltage across this transistor would be what? 0. Right? I'd go up, it'd come down the same amount, I'd have 0 volts across this. What region of operation would this guy be in? Linear, right? It's sort of linear, no current flow hardly, so it's got almost cut off too. But let's say it's linear. So what do I need to do? I need to go up a little bit higher. So I need to make this transistor a little bit smaller. So if I call the voltage on VD sat 8, whatever VD-SAT we get from this 2 over 1 transistor for M8. Let me have VD-SAT of 9 be equal to 2 times VD-SAT of 8. No, equal to VD-SAT of 8 plus VD-SAT of 2. Right? I want to have the VD-SAT across this guy equal to the VD-SAT of this transistor plus the VD-SAT of this transistor. Then what will this voltage come to? It will, if I do that, then the voltage at D2 will be equal to, I go up, a VT plus a VD-SAT. So let's say, let me write this up. Let me redraw that. See it. VD-SAT of 9 is equal to VD-SAT of 8 plus the VD-SAT of 2. Okay. VD2, now, I'll go up a VT plus this VD-SATs and come down a VD-SAT of 8. So VD2 will be equal to VD-SAT of 2 relative to VS. I guess it's all plus VS, right? Plus VS, right? Right? Start from VS, go up a VD-SAT, come down. So basically I'm having this transistor cancel out the VD-SAT of this, and I'm leaving left over the VD-SAT for this transistor right here. So this guy's in sort of the high swing mode. So we've biased up this cascode into high swing condition. High swing condition is that this is at the minimum voltage possible to keep this device in saturation. That's how I do it. So I got to design this, and so for this currents and so on, it turns out, for whatever I use for this example, this has to be 2 over 30. So this guy's a little guy, right? Because he has to consume the VD-SAT of this transistor right here. Okay. And so a small amount of current. It's a small amount. You don't want to waste current here, right? So to make that current small, this has to be even smaller in order to get enough VD-SAT to compensate for the bigger current that's going through here. And that puts this guy right at the edge. And as we change the common mode voltage, this is most important, this voltage will rise right up and down with it. You know, Vs is equal to Vin, common mode, right, minus Vt minus VD-SAT of transistor 2. So as this goes up and down, Vs goes up and down, but this bias always keeps this guy just right at the edge of saturation. So this is a good bias approach. So now we've solved the biasing condition in the bottom part here. What about the upper part? Could we have done a better job up here? Remember this guy here, he can only go up to what? This VDD minus VT minus 2 VD-SAT. That's the maximum positive voltage we can get here. Could we have done better? High swing. If we put a little battery here of size VT, we can drop, or I guess the other direction, right? We want to increase this by a VT. So instead of this voltage being at VDD minus VT, I can add this little extra VT here, and I get rid of this. So this can go all the way up to VDD minus 2 VD-SAT. So this is in high swing. So now we can go to a 2 VD-SAT of the positive, and I think it's a little more than, you have to worry about the VD-SAT of this guy as you go negative down here. So I think you have 3 VD-SATs in the bottom part here. So here's the message. You can always get rid of the VTs, right? The VTs should not be in, the threshold voltage should not be in your output swing limitation. Using these high swing techniques, you can somehow get rid of that VT, which you will be stuck with. And this you can't get around. You've got to at least keep a VD-SAT. So you can look at these circuits and you figure, is this topology going to work for me? You can just start counting VD-SATs up and VD-SATs down, then figure out how to bias this thing up to achieve that value. So you got one VD-SAT here, one VD-SAT here, and one VD-SAT here. You're not going to be able to beat that. So this thing has 3 VD-SATs in the negative side. That's a lot of VD-SATs, okay, right? And 2 VD-SATs up there, right? Can we do better? Anybody have a question about that? So this is a telescopic op amp, and you could do this in high swing, and it works pretty good. And it's pretty useful. This is a very good circuit. It's single stage, you get a lot of gain, and having, as we'll learn, having one stage is a really big simplification for stability. I haven't explained this yet, but let me just say it now. A multi-stage circuit like this can go into oscillation as soon as you have 2 stages or more. 2 stages on the hairy edge. A single stage circuit like this can never oscillate. So this one is a great solution for you if you don't want to have to learn all that stability stuff we're going to go through. And as we go through it, you're going to wish you didn't have to learn it. Okay, right? So, if you can stay with one single stage, you just solve the stability problem with the topology. You don't have to worry about all the stuff we're going to go through to make an op-amp stable. On the other hand, if you have to have a lot of gain and you can't live with one stage for whatever reason, then you'll have to go to these multi-stage circuits. There's a better circuit than this that gets rid of some of the swing problems and still a single stage. And that's what I'm going to talk about next lecture. All right, but let me just show it to you right now. Here it is. So this is the next circuit. This is basically a telescopic circuit, but what we've done is we've folded it. So here's the output stage, and we've managed to fold that output. So this is the circuit that's very often used, called a folded cascode. So we'll talk about it next time.